And now are the next impressive slides, which try to get some more meaning out of this data. So what you have seen right now have been static maps. Like a query, make a nice map, maybe you can automate it. There's not much magic about that, but we want to understand a little bit more what is actually the information inside these maps and how it is interacting, maybe how it is changing over time. If we have certain kind of assumptions, maybe we track the path, was happening there, when was A, then followed B, maybe we know what is C then. This kind of things we like to introduce now in this lecture. So, and this will be about the differentiation about models and systems, and maybe how we can bring it into urban planning, urban design, in a certain kind. Okay, what are models? Yeah, as most of you maybe think of, yes, models are something what you can parameterize, and then you can compute something on, and you can render it. That's true. That's basically it. Of course, you cannot just use 3D models. It can be like data spaces, whatever. It can be very abstract ones. It can be different kind of things. You can use it to simulate energy, wind flow, crowd behavior. You can make visualizations, data representations from this first output, for instance, and you can make changes, for instance. So this could be just a change in your building. It could be a change in a DNA simulation. It could be something very different. But all have the same if they're coming from different kind of disciplines, actually. All models are used, actually. When do we use models? When it is impossible and practical to have something real world at hand. So we, of course, for a design proposal, we don't build a whole city. We just do maybe some wood models or styrofoams or city engine models. And they are simplified. Models use assumptions. And our number and precision of assumptions affect, of course, the accuracy. And this is usually what we as urban designers have a bit as a problem. We're usually operating on a very, you can say it's an n-dimensional data set if you are drafting a new area, and you actually don't know all the kind of site interdependencies. But sometimes it doesn't matter, sometimes it matters a lot. And you need to have the feeling where it matters the most so that you have the right tools always at hand. And of course, models, as I said, don't need to be digital, of course. In comparison to direct measuring, direct measuring is just calling somebody, making interviews on the line, and asking, how do you feel? What do you like? What is the urban quality in your area? How can you go to the next shopping? And so on. You can only use it where you have like conditions, where you have experimental control on. And you can actually apply a scientific method for observation. And of course, the accuracy is higher on the modeling, but you need to monitor the errors inside. So there could be always somebody who makes something wrong in the survey, or your tracing method is not perfect. And usually here, the effort is very high. So sometimes it's much more easier to make a model, usually it is, than to make a huge census in front. So that's the reason why you should use models in planning. And even as fast as these models become, the more useful they are actually for planning. And to express this kind of modeling, what you're doing, you have this components, information, knowledge, and you have the systems connected. And usually all this kind will be defined or expressed by rules. They should be consistent so that you have every time the same. For cities, we have like 3 common possibilities to describe city models. Of course, CGA for city engine, which is more like low-level model information, very unspecific. Then we have a very high-level description, which is very graphically, but very uncommon for architects, UML, and which is looking like a lot like in Grasshoppers. If you have those visual components you put and plug together these things, that's something similar, but more generic. Of course, not to Grasshopper components. This could be used for modeling data sets, but as well for cities or processes inside a company and so on. And then we have something CityGML, which is taking a little bit out of that and a bit of geo information, but it's overwhelmingly complex. There's like 1,000 pages just of definition inside, so it's not commonly used right now still. Okay, yeah, what is a simulation? Yeah, actually it's a functional implementation of a model. So it means you can run this simulation to make a reconstruction, like a city model. You can run a simulation to run something over time to see some fluxes and changes. And ideally it should show you some insights on a particular object, testing, analysis, and training. And to have actually a model, you need to have a structure, of course. Without a structure, there won't be a system where all the kind of things are meaningful connected. And therefore, you need to have a recognizing process, recognition, observation. You need to find out what's the nature in the urban system, for instance. You need to find out what are the most stable development patterns and what will be the relationship of entities. And here, very funnily, it's very helpful if you have then the direct measuring actually as an initial input to create actually those structures. So, defines the configuration of items. In our case, for instance, in City Engine, we have streets, we have lots, and we have buildings on that lots, configuration of items. What are the interrelated items? So we have different kind of building typologies with different kind of windows, facades, and they also have a hierarchy. So a building sits on a lot, and building has some windows, and so on. And this is, of course, not just restricted to urban design. You have it actually, it comes from biological structure, so one of the first ones which just tried to explain systems, chemical structures, yes. Even musical compositions have certain kind of structures or behaviors, social structures, data structures, and so on. You find it everywhere. So, and the system is actually the composition of all that interacting elements that you have inside the structures that form an integrated whole. Yeah. So, as I said, so which is it looks banal, which is but very important. What are the components of a system? Very important is the boundary. The system is actually defined, where it starts, where it ends. And everything which is next outside the boundary is the environment of the system. So everything what is inside the border line is part of the system. Everything what's outside is part of the environment. So everything what you want to simulate with a system is inside, everything should be outside. Okay, so, and this is actually first generic model, one of the most generic models that you can imagine. So, and there are different sorts of systems. One, what had been observed in biology is, of course, natural systems, ecosystems. They usually don't have objectives, and output can be interpreted by related systems. So something, species A is contributing to species B. If species A don't exist, species B don't exist either, for instance. And man-made system has usually the purpose to deliver output, even if it's sometimes not so clear. And yeah, it's a coherent entity, or you have different kind of systems that are connected and bridged to each other. Okay, so just as a comprehension, open system interacts with its environment, and the closed system is isolated from its environment. It seems to be very clear, but this is necessary to be once posed here. So, where does it actually start in urban planning and in geographical planning? In the late 50s, there was like a quantitative revolution. Before that, somebody was doing like traditional drawings and assumptions and mapping techniques, but actually there was like another mortgage crisis in the 40s in the US. So they have quite a tradition on that, and they had really a problem. How did it happen? They didn't really found out what had been all the kind of dependencies on that. Why did some developments go obviously very wrong? And so some mathematicians put themselves together with geographers, and they wanted actually to query and to find something out, what happened actually there. So they brought the interrelation between spatial and mathematics, and those they created kind of systems, but very assigned to the financial components, not so much on social qualities or preserving natural reservoirs. It was really, really basic, just money. Yeah? And so it was the first where they got a connection between the geographical space and mathematics, and focus on urban economics and human behavior linked to a system approach. So, and this came actually to one of the first developments actually where interdisciplinarity was actually first occurred and actually first happened in planning. So that it's really like transdisciplinary systems engineering as a science that was really developed from this point. Actually, it's just, as you see, it's about only 50 years old. But actually, the first urban system had been developed some 1,000 years ago, like 500 before Jesus. There was the idea of the ideal perfect city. Of course, any kind of development beyond the Greek antique and the Roman antique, the ideal city always was something that never happened. But Hippodamus from Miletus, so he created Miletus, of course, did the first kind of very strictly designed technocratic system of planning a city, which was very kind of efficient and as well like a point of success for the Greek colonies, for instance. So the idea was make a city, and the city has a threshold of 10,000 free men. So with 10,001, we need to make a new colony. So, and including all the other people inside, so it was not just men. There, up to 50,000 people was actually the size of the city. So everything what was going beyond that size, they said it's not capable to exist as a city any longer, and so that there has to be a threshold, and so we need to spread, build a ship, and go away. So that was really like, yeah. And even inside the city, they had a social system. It was very simple, of course, for those days, and it was very technocratic. And I don't want to make any values if it's right or wrong, but it's a nice thing where you can make comparisons to today. They had like different kind of social classes, and the land use was very simple as well. You just had it more or less three: sacred, public, private. So, and so these are some examples of the cities that are based on the design of Miletus, of Hippodamus. For instance, Miletus was the very first one, rectangular grid, with a strong orientation next to the sea vents. So we had really like natural ventilation was always like on, was elevated. Here was the sloping in that direction. Here was it higher. There was more flat. And it was really like meant to be that you, even if you had this hot Greek summers, that everything was flooded with air. Knidos, for example, was as well a very nice example for that. actually most of the cities had been destroyed through some earthquakes and something else. That is something what he did not plan for. Okay. Another example, which was a more modern example of an idea or a model of a city, was, of course, Howard Ebenezer's garden cities idea, which was really what was meant differently. So later on, it was interpreted like was really like a site plan, but it is not. It was just a functional diagram about the interrelation between different kind of population distributions and how you can actually access better life qualities. So, for some points it's still valid. For some points, he didn't consider so much the problem of transportation. So, and the problem of transportation was neither considered by another very common and well-known architect, Frank Lloyd Wright, with Broadacre City, where he made a very extremely extraordinary patch of different kind of land uses where you need to drive like 2-3 kilometers to get to the next neighbor. And yeah, but it was really interesting because it was one of the the modernist answers of a kind of city system. And yeah, modernist age, car traffic network was the solution for everything without knowing all the other effects that it had. But on the more economical side, without so much dreaming and doing like the Dubai of the 30s or the 40s, there had been the development from the 20s of different kind of zoning models. So for instance, the concentric zoning, where you had the CBD in the beginning, in the middle, then you had the transition zone here, where some industry, slum-alike, later on ghettos like developed, and you had the zones of the working man homes. And the idea was you have a mixture between very high quality living and representative units. And then you have that belts around where you can make easily a shift in the usage. So there was really an idea to have low income and low social living standards placed next to the other one, which is really unimaginable for today. Then you have the idea of Kristalla, which was more on the regional level, that you have certain kind of regional focus points, and with each kind of point inside had a certain kind of attributes what they should actually have. A bigger city should have a university and a big university hospital. Smaller city should have a small hospital and maybe higher education. And the smaller ones maybe have something, shopping facilities, but actually not so much. So it was like as well one of the first approaches to coordinate economical developments. Unfortunately, it was a bit too strong connected with the German Nazis, and so it was like the idea as well to make a coverage for all the Gauss centers of German bureaucracy from these days, and that was therefore not so much liked after the war. But the idea was kind of interesting, a simplification of all these interdependencies, and as well taking all these kind of economic effects into side, just invest in the centers and give minimal invasion of potentials into the more rural points, but even to be fair with all this kind of topology points. Okay, the idea was that you have more homogeneous area, you have no topographic barriers, so it was a very simple model with a lot of errors actually. And as well, the transport costs have been not considered. And yeah, a lot of things was left out to simplification, but the idea was that you have a producer and consumer win-win situation. Actually, this is a very strong point. If you set up something like a development plan, who should follow it, you need to have the eye for that. Okay. Yeah, concentric zone model, already talked a bit about that. The polycentric zone model was like the idea what was learned about this very rigidness of this zoning models with the concentric ones, that it was not really working for all these pie slices here. The idea was to have since usually there had been already kind of a lot of developments existing, and if you go into a certain site and you have more or less patches of different kind of use functions, and sometimes it shifts over the scope of the scale, sometimes it's very the same. Zurich, for instance, is very fine granularity, and there was really the idea that you put most ideal patches next to each other. Of course, as well with the planned cities, they thought first it is more ideal to give some answers on planning problems, but still then it was not so easy. Another idea was like the idea of the polarized development for European cities mainly. So the first in pre-industrial ages, we had local development centers, and they have been all interconnected with one line, street network, trading network. Then later on, with the coming up of all the manufacturing centers, it was not possible into all those medieval cities to put it inside. You need to have it to spread it outside along the borders of the city, and then to interconnect that one. And from there, some of the centers grew up quite quickly, and some others had been the smaller ones, but with maybe some certain specializations, with increasing exchange in between. And this came to a much more differentiated means of transport as well between all these systems. And today we have all different kind of bubbles inside Zurich, for instance. We have a center with a strong point around the Bahnhofstraße and so on, but then we have all the little centers that go outside until Dübendorf, for instance, and are interconnected with the city. And therefore, it's very important to find out the connection between land use and transport. So there is a connection, inevitably, and if you do it wrong, this interconnection, you have messed up your whole city, and this is something very sad. And sometimes if you look at the highway situation in Zurich, for instance, this may be something like a decision in the 60s made that cannot be turned around today so easily. So, for instance, if you know the story, in the 60s there was an initiative actually to build a highway up the ground, under the ground, and later on all the traders, they said, no, we don't have to have like a highway because everybody will just bypassing Zurich. We want to have all the traffic inside the city because that means that we could sell and sell and sell and sell and retail. And so it came really to that situation that the highway stops at the entry of the city, and the traffic chaos starts then inside the city. And this is just because at the wrong point of the history, there was a decision made. Yeah, it was not so much helpful, maybe. Okay, so, yeah. Actually, it's difficult to isolate land use from transport. Yeah, it has all influenced each other. And the idea is actually, in the end, that we want to couple the human decisions behavior to some mathematical models so that we can see. For instance, there are like prediction models for Zurich. You can exactly say at 8 o'clock in the morning in Zurich, there will be some agents traveling through the Zurich traffic model, and it really looks almost like Zurich looks like. Okay, so based on empirical surveys, as I said, you first need to make this direct measuring method. Then you make the quantified conclusion, and in the end, if you run it, the results are of course, not more universally valid than these empirical studies, since it's based on the studies. So, to come up with the change process, actually, we don't have so much chances to do something, actually. Very slow changes to urban transport, communication, and utilities. If you mess something up here, it will affect the city forever. So, for instance, Sao Paulo, the boom town of Brazil, at the moment it stops actually to progress economic growth, because it's just the traffic is congested everywhere, and it's not possible to change so much in the next years actually. Since in the last 10 years, 15 years, it was impossible for the city to plan ahead for all the changes. So you have similarities in China, but in China, so really the government invests from Beijing, every kind of little tiny, not really tiny, but centers which are developing quite rapidly, really first invest in some transport mean, even if they don't know which kind of transport mode it should be, if it is railway or street, they just first invest into streets, even if they go to nowhere. But at least they have streets. Okay. So where do we have chances? So we have the possibility, fast changes in employment, shifting the people around, and of course, how to steer something in real time, and somehow as well as the workplace and the housing. If we do it right, we can as well from here influence all this behavior and all that behavior. So that's very important. We have our stake actually. So if all the people feel very relaxed and very well in our environment, they won't have the need actually to go outside on the weekend, to go somewhere else. And so to say, on the urban environment, what are the more critical ones? Of course, what you can have immediate as the transport noise and the air pollution. You can change it, and you can have it very immediately. What is very problematic is water and soil contamination, and very slow. And the most dangerous are the effects to climate inside the city and on Earth. So what we have as well at the moment, we have those urban subsystems. There at the moment, as I said, they are basically market-driven. It started in the 50s. They started first with Washington, with the metropolis calculation. And they try to model the interdependency between accessibility and activities of the users, and accessibility for the transport. So you have this passive and active use. And everything is interconnected with each other. And this diagram shows it actually quite nicely, how these things are put together. So from there, they arrived at a so-called location choice model. And the idea was that you really couple service and retail employment location, and you had as well a first model that evolved in several other ones. And at the moment, for urban simulation, for all this land use and transport connections, there exist just 20 models worldwide, basically. And at least 2 of urban subsystems are incorporated, and just a few of them integrate like very holistic 8 subsystems. And which is very interesting, the urban environment itself as a built structure is mainly negotiated. Not existing here, neglected, sorry. And this is really a problem. So if all these modeling processes run, in the last point of view, actually only the urban designer comes into place, when actually all the regulations have been already made and hand over from the planning authority as actually the policy that should be followed. And that's too late. Because a lot of things here from all this calculation are left out. Urban qualities and different sort of things, just to name a few. So that's just a list. These are the nice models that exist somehow. And some of them we use, and one of them we use in our own research work here, Urbanism, for instance, and colleagues of ours, MetroSim, and which is not stated here is MatSim at Kai Axhausen's group. Yeah. And the idea is actually that you really have to understand what are the parts that are change fast, which are slow, and how is this interacting with your environment. So first you need to be aware of some parts of mathematical and statistical models. Then you need to be aware of the analysis of the existing structures. Then you want to predict structures. You have certain kind of ideas how development should go in which direction, and which are the successful developments that you could use as a best practice, actually. Perhaps the result of that, if you put it right together, you have a very abstract GIS system where you can put some data from your cadastral data, make your design draft inside, and find out if it was good or not. If you make then a prediction over time, what your design actually affects the system. But as I said, usually you have like this big scope here, this international scope, then you have the regional scope, then you go down to the raster cells, but then you have all those very nice calculations done, but then what's about urban design? Nobody has an answer to that. And actually, the idea here, how in planning are problems defined and later a plan is evaluated, is very similar how it is done actually in science or in geographic modeling. So we made, for instance, 2 years ago, we made a very simple grid cell-based simulator of the specifics of the Greek ancient cities, the automatism to place a site plan according to the topology and the land use mix. And very interestingly, it really computed almost the same layout of the Malaysian cities in the end. Some of this very, very simple building typologies have been used to create visualization out of a little city here. So, and so this could be like developed a bit further, and it was really developed a bit further with colleagues from us from UCL and Purdue University. Maybe some of you had seen some lectures of Daniel Aliaga, who was guest professor here. And this would be in the next part, the last part of this lecture today. So the idea would be that we have like a system which delivers the definition of scenario. So you have to deliver it. That you have to create a feedback, a visual feedback for stakeholders. They can create as well some feedback on that, and that you can report on performance indicators. So maybe for the last part of the lecture, you can maybe remember one of the last lectures where I showed all those procedural methods and so on. And then we have urban simulation, where I talked about the initials and all those basics and the GIS in front of it. And as you know, for the urban modeling, we have like information like roads, blocks, parcels, buildings, and in the end we have a 3D model if you combine it. So, in the urban simulation, as I said, all this economic modeling, you have population, you have jobs, you have maybe accessibility to something in a network. It doesn't need to be just traffic. And you have the land value. And then you get out of the simulation a land use distribution. So wouldn't it be nice if you just couple everything together, that you have an integrated view, that you have on the one side you have the nice model, on the other side you have this land use allocation simulation for the year 2020, for instance. And so that this should really interact with each other. So, and that you have, for instance, where you have where the likelihood is high that you have a high population density and job opportunities there, that may be like the density may be a bit higher, if it makes sense at all. And somewhere where you have a lesser interconnectivity and accessibility to all that, maybe the density doesn't make sense to make them to actually hit the density high. And if you see that you can actually calculate it on a city scale, this could be very useful to find out about future trends. So, to get a bit more in detail to that, I just will show you a little bit an overview on that kind of urban simulation approaches. Then how this is actually integrated, computer graphics meets urban simulation, and how it can be used in a first open source real-world urban planning system. So, as I said, this modeling was already covered, and now simulation, to give a brief overview. So as I said, mostly urban simulation is tied to the economical perspective. So in this case, most simulation approaches takes the use of agents. So you have agents for jobs, you have a population, and you have housing units acting as agents, you have the land use distribution. And yeah. So I already showed, I think. And so like these are three common techniques. Like we have the cellular automaton, you have the agent-based models, and last, which is the most evolved one, is a dynamic so-called microsimulation. And a very nice example system for the dynamic microsimulation is Urbanism. The cellular automata is actually, the idea is that you have a conversion of non-urban land to urban use. So it means there's something like game of life-based thing. The one pixel eats the other, and then it turns over into not being farmland any longer, it's just urban land. And sometimes you can spread inside this urban land something like Zersetzungsprozesse, and then you have something falling down of the urban structure. And actually it's just a tessellated space. Tessellated means you have just a grid space where these automata are eating themselves through, and all the simulations runs, of course, over time, and there's an exchange between the cells and the connection between the next neighbors in the cells. But what is not covered is we don't have really covered the changes in the built environment, or actually the inhabitants are covered, and the time, the traveling situation is not covered at all. So usually it starts like this. You have like, yes, very nice input, visual input. Oh, crazy. You have like this first development zones annotated here. And then you let the algorithm run. Then you have a change. And maybe after 25 steps, could be 25 years, for instance, we have like a spread urban development like that. These are natural barriers, for instance, what you can include. Maybe you have some pollution sources that will be avoided for living, but not really much. So you see the cleverness already of this computational approach. And then you can make some nice art images here about the spreading of the different kind of land uses. And we can compare the simulated with the ground truth data with what was happening in real time, real world. And maybe from this regional perspective, it's very regional, it's covering something already, but it's very imprecise on an urban level. These are the major publications for those ones who want to check it out and maybe make their own solution. Okay, the next one was actually developed from that, was the agent-based models. The idea was to extend this automated cellular automata framework with so-called mobile interacting agents. Instead of just having one grid cell eating the next one, you had some agents with a certain behavior, like it will move from A to B and maybe backwards again. So was very simple behavioral rules inside, and but the problem is that you get trapped in the local context sometimes. So if some local boundaries are reached, there's even animal behavior for these agents, and they won't get out of it. They're really trapped inside. And then we have the micro-simulation. This was the idea of combining the urban economic analysis with the modeling of so-called choices. So you have a discrete choice model. It means if an agent comes to a situation B, it makes a choice out of C and D, and then goes maybe to the next location where it has to do some choices again. So it means at morning, 7 o'clock, I have to wake up, and then at 8, I have to leave home. I go by bus, I go somewhere else where I should live and work. So statistical triggered somehow, there's the most movement between A and B. And yeah, in the end, it comes to this. And yeah, maybe one of the most advanced systems is actually Urbanism, which is open source. You can download it, but it's very hard to set up without knowledge about that things. But what is very interesting in Urbanism is you can really simulate the choices of individual households, businesses, parcel landowners. You can really describe development scenarios, and yeah. So, as I said, you have the differences in between is the discrete choice method. You have explicit representation for the real estate market, and you use statistical methods to try to really calibrate with this one's the model system. So what you can take out of it, you can find out where you should do actually the next traffic investment, maybe where you should prohibit land development, and maybe they need to find out something about environmental protections. And in the end, there are very abstract maps that comes out of this computation that can be used as an input for policymakers, public, and so on. Okay, so this would be the Urbanism part. And here we go over to the visualization. So what are the traditional visualization methods? For instance, a very standard one is the creation of thematic maps or chloroplast maps, where you show certain kind of values. Oh, I should be faster. I'm running on reserve battery. You're so out of luck. Hat jemand ein Netzteil von euch? Aha, okay. Ich habe gedacht, ich bin schneller fertig. Danke dir. Das ist ja richtig gemein. Der weigert sich ja dann wirklich, die Präsentation weiterzumachen. Ne? Ja, klar. Danke dir. Okay. Yeah, so basically the areas are shaded in proportion to the values of the variables. So in that case, income in the Puget Sound area. Another method is to use cartograms. If you look at a traditional map of the US, for instance, you see, oh, big country. And if you see, for instance, like the results from an election, oh, Midwest, not much Democrats, maybe. And but if you really look at the population size and then recalculate, then something happens very interestingly. That there's areas around the coast which have a very high population density really shows the image actually what the US is looking like from the potential of the voters actually. So this is very interesting thing. So you still can somehow find out that could be US, but you have more insights about the actual values. Another approach is, for instance, that you make a section through the cities, through different data sets, and depending on that you create a focus-aware city model, that you only, on the actual state where you are, you create the optimization of, you can actually reduce the polygons. Focus-dependent, multi-resolution, still looks like a city. So for instance, you have this was in those days when computing a city model of the size of Zurich was unimaginable, so you need to really reduce the data sets. And on the one hand side, you had still the geo information, like here, simplified one. On the other side, you want to have a 3D model, and you want to mimic, actually, it's like a compression method, actually. You want to mimic, actually, the structure still, so that you can have actually a look on the whole city. So, another technique is an urban visualization is a kind of geographical weighting. So how does this location, how is this location compared to this one, for instance? Yeah, if you have different kind of parameters like jobs, distributions, and you can all see the different kind of differences from this area to that area, for instance. So this will be like the median, and this will be lower than the median. Everything this is higher, for instance. So another one, what you have been already seen, I think, is the visualization of already kind of simulated urban spaces. So the idea is with like texture patches, you create an output with a structure, with a system like Urbanism. This is the current situation of the current satellite map. And then you have a change over the time, different kind of parcels, parcel zones, and you just fill it up with another satellite information according to the land use change. For instance, here the park had been eaten by the city. So, yes, so this would be the shift in the spaces here. Okay. And how does this happen? This was one of the first attempts to really couple visualization with this abstract sort of modeling visualization, with this abstract simulation, where you had the lower one for the urban simulation combined with the upper one for the urban modeling. So, hello? Okay, yeah. So this has some results from here. You can really see the different kind of land uses. According to the land uses here, the different kind of parcels had been accommodated. It's just 2D textures here, but for quick drafting of land use policy changes, it's maybe very interesting. Another result here is a computed image here. So this is from a colleague of mine, from Basil Weber, where he started this in his master's thesis, a project where you can simulate urban growth. For instance, this is Las Vegas, so the rules of Las Vegas in this case, how different kind of land use properties had been developed over time along the strip here. And you can really see, you have this time progresses here, and there should be actually an image where you can actually see, yes, you have this optimization function for the land use. When land use A will be put into place, then it comes over the time to addition of the population development, then it will be further extended next to the street network, and so on. If you see here, you have the original plot, and here you have the computed plot. Maybe he has tweaked something, but it still is working very nicely. But it's only fast-forward computation. It doesn't make any kind of interdependencies inside. So here we have something what we call Urbanism, because it was developed in the Purdue University by Carlos Vanegas. And this is a quite nice tool to set up quickly on a kind of information visualization based, more like a diagram, development diagram, a city structure. You can set up certain kind of main access roads, for instance, a main street grid, and define different kind of population sizes, and maybe even like natural barriers, what you have here, for instance. So I think this would be like the information for population density in the beginning, or job opportunities in the beginning, and then maybe like 20 years later you have a higher concentration in different kind of centers, and then you get the computed result from this one here to that one there. As you see here, you have a little spreading now around this corner here. And this in a kind of very intuitive and interactive model. So if we make it on time today, then we will try this out in the exercise. So the idea is that you have on the one hand side, you have all the kind of geometric modeling. So we can actually say we know that a little bit from the city engine. And then we have on the other hand side, all the different kind of mechanics of job and population, accessibility and land value, blah, 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 economics. And then we have the GIS information given to both as an input. So, and those are coupled, like highways and accessibility makes sense. There's higher accessibility, then I can even go far away for getting a job. And if the land value is lower, maybe if the traveling costs are not so high, I want to live in the outskirts and so on. So this is actually working quite nicely already. And the idea is that you have a grid where you have each grid is representing a set of variables. Here. And this set of variables has like has values for different kind of domains, like transport, population size, job distribution, accessibility, and you always go along the grid where the effort is relatively low. So, like you would do in nature, maybe where you have low effort, and you want to have maybe a big house on the outskirts, or you want to have the city life inside, or something like that. What all your personal premises are, then you will make your choice. And these things are actually filled then with possibilities. And like we add new jobs to the queue, and then the jobs will be relocated depending on the traffic network and with the interconnection to new possibilities where you can actually create households and homes. So it happens like that. Initially, you have a seed of so-called seed, and then with an AND-based algorithm, the seed will get interconnected arterial roads, and from these arterial roads, you have a refined block roads and inner quarter roads. So there are different kind of looks that are possible, styles. The computer graphics guys, they always refer to that as styles. For instance, a grid-based approach that you can add tortuosity. It looks more and more organic. And then you have like radial styles. You have those very interesting traffic corners in the middle. If you add tortuosity and you add terrain to it, it always looks almost like a city. So some results you can understand as like set-ins. It's not really that you have the control like in City Engine, that you have different kind of parcels and you can structure your parcel. That level of design control was here not in focus. It was more like that you have certain kind of prototypes, that these prototypes are automatically generated to represent, for instance, a business district. What was this? Ah, crashed. Nice. So actually, I didn't connect my computer with the touch, so something new. And it's the same with the living units and so on. And for some parts, if you make a nice overlay with different kind of textures to it and you make a color calibration of the system, you can really say it almost looks like the same city, if you compare it to each other, but it isn't. So, of course, for certain users, it will be okay. So, for instance, if you just want to make a prediction of certain kind of development scenarios, it would be very nice to just see something in the very beginning. The setup costs for that systems are very low in comparison to all of the others that I know, and from that, having that in mind, you can use this as a potential input to get some insights. So, and now this was like an early prototype, and now it comes to the Urban Vision project, which has been developed by Paul Waddell and Daniel Aliaga. Paul Waddell is actually the inventor of the Urbanism system almost 10 years ago. And he had always the problem that his visualization that he did was like all kind of this typical map things that I showed you just some slides before. And Daniel's strengths otherwise are, of course, computer graphics. And it was now interesting to couple those with this powerful system of Urbanism, which does all the kind of calculations and all the means of interactivity that are possible actually with computer graphics, what Daniel knows best. So the idea was really they just made this project happen within, I think it was like it started in January and stopped in September for the first run of the project. So the next phase of the project will start then soon. And they really set up a connection between Urbanism and real-time evaluation of the scene that can render actually a whole city, like over 7 million people. And the one thing is the simulation scenario, and then is the areas of interest, so to say. So beforehand, we had all those different nice-looking maps. Nobody really can understand. So only it's limited to tables and databases, and you don't really have immersive navigation. Otherwise, you see like zoom and panning like that. And you cannot actually incorporate the feedback from stakeholders, and therefore there was the idea that you have something 3D-ish that accommodates certain kind of building typologies, very simple ones, into a massing model, which can be, of course, textured and add more detail, but connected to different kind of land use. So all these different colored patches are actually representing different modes of land use. And you combine this with behavioral simulation like it is done with Urbanism. So this micro simulation. So you have one run maybe where all the different kind of allotments are computed and the land use types are assigned even based on real world map data. And then you just create on top as an interaction with that the three-dimensional visualization. You just link those typologies to these computed values. And then you get something very nice here outside. You have even traffic simulation. Unfortunately, I didn't have the video of Danny. I have to ask him once more. We even have traffic simulation. Cars are going along and people are running around. But it's not SimCity. It's even more. It's not the same. Or the Sims. So now it is the first prototype has been made between Purdue University and University of Berkeley. And then later on, it's really meant to be that we are here at ETH or our friends in Singapore or EPFL, the users as well. So it was first used for the at the Bay, at the Metropolitan Transportation Commission, to have some future development scenarios at hand, how you actually can use this for sustainable planning. And yeah, later on will be implemented for other cities and communities. And yes, okay. So I think now we have a kind of very intense and broad overview on GIS, urban simulation, and modeling. And maybe it's time for half an hour break. And then we meet again in the computer room. And I give you a short insight on GIS system, ArcMap, industry standard system, how you can link that with city engine model. And then you will get some exercises. And maybe if you have some more time, we'll do the Urbanism, what I just showed here as a live example. Otherwise, we'll do it next week in front of the Ecotect exercise. Okay, see you soon. Sorry, do you have questions? I forgot. Where's the coffee? Do you have any?
One thing I was wondering about is there seems to be the ultimate direction is then these improved visualizations, but actually, which is good for communication, but to translate all of that into documents, say legal documents as part of the planning process, it might be more useful to produce beautiful maps, to take all this data and produce good drawings.
Okay. Basically, the idea is in front, before you make all those legal documents, that you have a holistic insight on what's actually needed for your legal documents. And therefore, these visualizations are very important because the lowest level of interaction in between everybody is to look at something which is very common. The picture of a city is very common, where you can put in all your fears or your hopes inside and make that scenarios where different kind of disciplines actually, even if they have different languages, can actually talk with each other. And then the idea is, if you have gained a conclusion on that, like stabilized the scenario, then you actually can extract from that the legal information. And maybe legal information doesn't need to be then more or less text-wise as it used to be. It can be maybe enhanced and accelerated as well by more descriptive visual information as well, or maybe even like with a testing system. So even if you have those parametric systems, you could even imagine that later on there may be a process that you could put in there your design suggestion, and you can see if it fails or if it is correct to that kind of legal things. So this could be was it like answering your question? So this is actually the main idea, that you have more and more interactivity, that you really get a holistic conclusion on what's really going on. And that's the main problem today, that you don't have any interaction actually, to be honest. Okay.